Good morning, everyone. So today I would like to give you a sort of an overview talk about high-resolution capabilities of ambient atomic force microscopy and the type of resolution that you can get on part systems AFMs. I'll present a couple of case studies where we could look at the sort of single molecule resolution at different types of sort of samples, some popular samples that people look over the years. But I think when I was going through the slides yesterday, I thought I'm going to start with the slide which is very unconventional for scan and probe microscopy, but I thought it kind of could make a really interesting story, and just to show that the high resolution that we often talk about is actually a really central problem in various different areas of science, not just in scan and probe microscopy. And in this instance, in astronomy, for instance, here we have an image of an iris nebula. I took it from my garden some weeks ago. And for many decades, that's what people saw, and they assumed that the nebulosity around the star was made of small particles that scattered blue light, because blue light scatters very well, and that's why it's a blue reflection nebula. But a few years ago, a Hubble telescope took a high-resolution image of that particular area in that photo here, and then scientists, to their surprise, the astronomers, they realized that things are a little bit more complicated than we thought them to be. And they found lots of red filaments within that blue nebulosity, which was completely surprising to lots of people. And then they realized that those red filaments, they actually emitting light rather than reflecting and scatter the blue light from the central star. And when they did further spectroscopic studies, they realized that those filaments are made of polyaromatic hydrocarbons, and they found even fullerenes in that. And the moral of that story is very simple. The more you look at your object, the more resolution you gain from whatever samples, objects you're looking at, the more you see. So coming to the AFM, which in a way, it's very similar. It provides you with a powerful way at looking at the materials and resolving not only the structure, but the properties, as for instance, Professor Jacob showed in her beautiful talk, that you can probe things at a really single molecular level. And here I want to give you a brief, perhaps a very basic introduction. Why is that AFM so important compared to many other techniques that we use to characterize structure and properties on this on that nanoscale? The most and really important advantage of this technique, it provides you with a real space imaging, and I can't really overestimate that much. It gives you a way to see things the way they are. So compared to diffraction techniques that provides you with a reciprocal space, and then you have to make models and get some kind of assumptions of how things are. With SPM or AFM technique, you can actually visualize single molecules, atoms. Critically, you can follow their dynamics. You can see how those structures evolve depending on the external stimuli and so on. Those measurements are highly localized because you use a very sharp probe. So the measurements are coming literally from a few nanometers or a couple of nanometers of your surface. They're damage-free, so you do not need to damage your sample to get that information. And because you're always interacting with your sample, you can do functional imaging. So you can probe nanomechanics, like in the previous talk, you can do single force curve experiments and measure interactions between single protein molecules. You can measure electrical and now spectroscopic measurements. And critically, in principle, there is no limit to resolution. So it's a technique that provides you really limitless resolution capabilities. And at the heart of all that is AFM probe. And this is a TM image of the very same probe or type of probe that I used in a majority of those sort of data that I will show you on the next slides. And the important point with that TM image that was taken some years ago by Michael Fay and Chris Parmenter here in Nottingham is that when you look at the very, very end of the tip, you see nano sort of structured roughnesses. And these are little features that, despite the tip radius, which is around about 10 nanometers, that's the way the manufacturer specifies it, those structures actually helps you to achieve that high resolution. But the biggest problem is that for decades, ambient atomic force microscopy really suffered from poor resolution, and many people are still convinced that AFM is not really that great and it only generates you some brown blob images. And it's kind of surprising how it's been kind of going like that for many, many years. So here I made a quick overview of some techniques that provides you with more or less routine high resolution imaging on ambient AFMs. And perhaps the first one, and actually that was a technique that inspired me some years ago and made me actually believe that with the ambient AFM you can achieve the resolution that was thought to be the usual sort of STM type or some kind of ultra high vacuum type resolution. So that was a torsional tapping where Nick Muller and Jamie Hobbs introduced the use of T-shaped cantilevers, and by exciting their torsional mode, they can probe the molecular structure, in this instance polyethylene. And these were the first images where not only they can see single molecules, but they could observe molecular defects with the just an AFM probe. So that was quite a breakthrough in the AFM imaging. Then there was introduction of bimodal tapping. That was introduced by Roger Parks and Ricardo Garcia, and there's a number of papers, one of them a few years ago, where again they used a technique to look at polymers. Quite often sort of those techniques were applied to polymers. And then a couple of years ago another approach was introduced, and that is high eigenmode imaging. We published a paper a couple of years ago where we could use that technique to visualize CH3 or methyl groups in the polythiophene on the surface of sort of a solar cell, effectively. And that technique was equally applied to other polymers like azotactic propylene, where you could see single polypropylene molecules arranged in a lamella. And the idea of that technique that I will talk a little bit about is the use of a higher eigenmodes of a regular or pretty much any cantilever. And in a nutshell, the beauty of that you can actually use extremely low as few or even a couple of angstrom amplitudes on your cantilever, and that is because your effective spring constant for higher mode goes a lot higher than you would have like for your base eigenmode. In case of, for instance, the third eigenmode of that type of probe that I showed you, TM image of the spring constant is in the range of a few hundreds of newtons per meter, about 600, I believe. And then the actual probe that tests your sample oscillates. It's only the very small portion of the probe that oscillates. So you turn in a gigantic probe, which in this instance is 200 micron long probe, you turn into around about 15 micron probe, and then you can use those tiny amplitudes. And that approach, as I will show you, provides you with really unprecedented high resolution in almost all media, ambient or liquid. So the beauty of that is you don't need any special cantilevers. You can use very regular, in fact, the cheapest cantilever. Majority of the images I will show you today were taken with the cantilevers, silicon cantilevers from budget sensors. You don't need any changes in the hardware as long as your microscope is capable to excite cantilevers at the sort of megahertz frequencies. You're set. It works beautifully well in any environment, and we tested it in air, liquid, and you name it, and it works on pretty much any sample. And be it the rough surfaces or soft surfaces or some crystalline and so on. And here I'll show you some gallery of examples. First, we'll look at the very demanding structures, the supramolecular structures that used to be usually sort of imaged with this STM, either in some liquid or vacuum environment. For instance, Trimesic acid that forms the honeycomb structure. You see single molecules here. When you put that molecule on the, for instance, graphite surface, and you can image it here, and you get that beautiful honeycomb arrangement with the period that matches exact published data for both crystal and works done in STM. Same goes for another network that I will describe a bit more in details later today, is a melamine cyanuric acid network, where the network is a lot smaller, just 9.8 angstrom periodicity. Then same goes for the real world polymers, because sometimes people say, okay, well, these are flat samples. How about those samples with the high roughness? So that's a piece of polypropylene that you use in packaging and things like that, and then you go and you can see molecules on the lamella, and then you can zoom further and take that 50 nanometer scan, and you can see single polypropylene molecule right at the edge of the lamella, and you can see how the polypropylene molecules go in and out of that lamella. Same, for instance, a Teflon, a piece of plastic tape you can buy from any supermarket. We image that, and we can see single PTFE molecules arranged in lamellas with a 5.6 angstrom resolution. To put you in perspective, the width of that line here is about 2.4 angstrom. That is sort of roughly the width of the PTFE molecule. So, but that technique, again, is not just about molecules. You can apply it for things like 2D materials, and you can image quite successfully Moiré patterns on things like van der Waals heterostructures. And here an example of graphene layer on hexagonal boron nitride crystal that I'll talk a little bit later about. And the same thing goes for biomolecules that we'll again mention today, where you can resolve molecular structure on the complex bioinspired peptide nanotubes, for instance, made of that molecule diphenylalanine. So it's a really, really versatile technique that can be applied to a variety of different samples, and you can get an angstrom type resolution in different environments. Okay, so first subject is imaging molecules on surfaces. Well, why do we want to image those molecules on surfaces? First, people use to absorb molecules either via chemisorption or physisorption to modify the chemistry in a controlled way. So if you want to control some patterning on the surfaces, that's the best way to do. It provides you with a precise and actually extra precise way to control molecular adsorption. So if you want to place molecules on the surface in a particular fashion, you can actually build molecular networks with a certain porosity, and then guest molecules can adsorb, and that's been shown with a number of different techniques. You can also build 2D organic materials through a coupling reaction. So when you adsorb molecules on the surfaces and you make them react, and you can make extended covalent macromolecular structures. And the other thing that we published a couple of years ago, you can build organic van der Waals heterostructures similar to 2D materials, where you can build layers of organic molecules in a very controllable fashion. So let's get to the first one, is melamine cyanurate or melamine cyanuric acid network. If we take two molecules, very small, just a few angstroms in size, melamine and cyanuric acid, and you put them on any atomically flat surface, they form a triple hydrogen bond between oxygen and hydrogens in the two molecules. And then we have that molecular motif made of those alternating melamine and cyanuric acids with the period, as I said, just 9.8 angstroms. So let's go to experimental details. So if we look at the large scale images, so we absorb those molecules from water on graphite surface, and then we image them in ambient, in air. So depending on the surface coverage, and that could be varied in a very sort of controllable fashion, from a tiny submonolayer coverage to a multi-layer. In this instance, we have a nearly monolayer coverage. And in the height, you can see islands of the network. And in the phase, you can see a contrast sort of corresponding to the height channel. Nothing really exciting here. But what was exciting to me is when we applied our sideband Kelvin probe force microscopy technique, which I hope you had a good hands-on session yesterday with Ilka. We discovered that with the KPFM, you can actually resolve a very nice domain structure that otherwise is very difficult to access, and something which before I thought there were continuous islands. In the KPFM, either surface potential or in the work function, we can get really beautiful domain boundaries between those molecular layers. And we can even see the work function difference between the molecules and the surface, which is around about 120 millivolts. Okay, so these are large scale images. What about the structure? If we zoom a little bit into that, and the first thing we see the Moiré pattern, because the Moiré pattern originates from the mismatch between the molecular lattice and the atomic lattice. We see 10.8 Moiré pattern on the surface. But on this image, apart from the Moiré pattern, you can also start seeing the molecular lattice. And if we zoom a little bit further, that molecular lattice becomes really obvious. And we can measure it to be 9.8 angstroms. Again, that's something that was performed using that higher eigenmode approach in air, and that type of resolution.
You have 3 minutes left.
Pretty routinely. If we go a little bit quick, we can get similar type things on other molecular structures like Trimesic acid that I mentioned before. Not only we can observe the molecular network, we can actually visualize the single molecular defects and areas with a sort of loose molecules, and zoom and actually see single molecules like we can observe here. Okay, the most probably exciting area with the SPM imaging biomolecules and bioinspired structures. And here was an example that I gave a hands-on session a couple of days ago of looking at the diphenyl alanine nanotubes, where you can get first, of course, a high-resolution nanomechanical structure, but then you can really go into the single tube and image a small area, and you can visualize those interesting lines running along the principal direction of those tubes. And you measure 1.22 distance between those lines. And when we compared that to the known X-ray diffraction data, we found that we have a perfect match between the macromolecular X-ray diffraction data that was taken in bulk crystals of the very similar sort of material, and our highly localized, high-resolution images of the same sort of systems, but taken on the ambient AFM. So with the molecules running along the principal direction of the forming rows and running in the principal direction of the peptide nanotubes, measuring the same number. So we measure 1.22 in AFM, and the same number comes from the X-ray crystallography. That is really remarkable. But we probed that property on a nanoscale, on a few nanometers, as you can see here. The same logic applies an image in 2D materials, and there's a typical example of graphene adsorbed in a hexagonal boron nitride crystal, a very typical situation. And when you adsorb it, you have a lattice mismatch between the graphene layer and the underlying crystal, and that gives rise to Moiré pattern. Like here's an example of different Moiré patterns from geometrical structures. And to move forward, we can probe that Moiré pattern locally on 2D materials, and there's different types of Moiré pattern depending on that mismatch. But what is interesting, you can actually manipulate that Moiré pattern. So you can go in the area, with two different types of Moiré patterns, and you can see wrinkles and some other bits and bobs and some blobs. And you can iron down it by scanning the same area at an elevated set point, and you can actually create a uniform, perfectly matched graphene layer with the same Moiré pattern. And you can take a larger scan image, and it shows you beautifully well-aligned graphene layer on boron nitride. Okay, so at the end, I would like to stress that with Park Systems and Next and the now FX series of AFM, we provide perhaps the best solution in terms of the highest resolution imaging, and that was demonstrated on things like supramolecular networks, which is a 3-angstrom layer. If you think about that, just a 3-angstrom layer on the surface of 2D material. Same goes for real-world polymers like polypropylene. I showed you a single molecule that goes into lamella, or semiconductor polymer like this polytithene lamella that we can image beautifully on 2D crystals, on biomolecules like on these peptide nanotubes and 2D materials. So we can routinely observe molecules, molecular defects on both crystallines and amorphous samples as well. But what is also important, we can scan fast both in air and liquid and follow dynamics here. So there's 2 videos. One shows the fast scanning of a Moiré pattern, which is static but shows how fast you can go. It's a real-time videos, just a print screens from the software, not modified in any possible way. And the other one is the solution of inorganic crystal gypsum, taken in the very same AFM, where you can show, you can see how the crystal dissolves in water by using the same technique and follow the dynamics. So at the end, I would like to thank you all for your attention, and remember, science should be beautiful. So we started with stars and we'll end with stars, and here's an image of baby crystals of potassium phosphate growing on mica. So thank you very much for your attention.